Before I continue with the lecture, are there any questions from yesterday? Yeah. Yes. Yes. Okay, the question is about the universal approximation theorem, that we heard that a feed-forward network can approximate any function in arbitrary precision. And this is done by giving the network, or actually the theorem doesn't say anything about how we can find the network, the weights and the size of the layer to actually represent that function. So it's not known, it's not a constructive theorem. If you don't know the function, then you cannot do anything, because then you can, maybe you have unsupervised learning, you find structures, but then the theorem does not apply. You don't, you have examples. Yeah. I'm not sure, but I think there are possibilities to do that, yeah. Yes, so you can predict the function at other points where you don't know. That's what the network would do, yeah. Yes. Yep. Okay, are there more questions? If not, so then let's continue. So as said already, the universal function approximation, this is a theorem that tells us, okay, it's possible, but it does not tell us how, what we have to do to actually get this approximation. And also, it's very impractical to learn a huge network with just one layer. And that's why people usually use feed-forward networks with many layers. And this is where we're entering the regime of what is called deep learning, where you have a network with really many, many layers. So I do the sketch again. We have the input layer here. So this would be layer L equal to the input is 0. And then you have hidden layers with different number of neurons, for instance here, and some connections. This would be layer 1, this would be layer 2, and then it continues until in the end you have the output layer. And this is denoted by capital L. So I said this here is the input, the first one. These are all the hidden layers. And this here is the output. So here I feed in my examples, which I also always denoted by X, I for the different components. There are n components in the input layer, and this is at the same time Y in layer 0. So here, all the values the neurons have is Y layer 1, here it is Y layer 2, and at the end I have Y layer L, and this would be the output. So like it's the Sn. Okay, and the weights here in between, they get also labels for the layer. So this would have a label 1. This here would have a label 2, and so on. And the last connections here, they have a label L. Okay, and then if I want to calculate the Y at intermediate layers, it's as usual via an activation function which sums up all the incoming signals from the previous layer, L minus 1, okay? Times the values the neurons have in that previous layer. No, it's like that. So from the previous layer, the values times the weights for into that same layer. And then you can also have the thresholds. So it's still the same that we have written down earlier. Now you have just the labels with the layers. So layer L, the Y's are calculated from the previous layer, L minus 1, as input, and the weights into these neurons. And there's also a threshold which can depend on position and layer in general. Okay, and we do the same thing here as before. We have a training data set. Xi mu with the target output St, and the mu labels the number of data sets we have. So we have capital P data sets, and we learn via gradient descent. Exactly like in the single-layered perceptron, with the energy landscape, which is a sum over all outputs and their comparison to the output we want to have squared. So it's also the same as before. You have the sum over all input patterns, and you compare the output produced by the network with the output you want to have, the target output. And the square gives you the energy function. So this Sn here, which the output the network produces, these are obtained from the activation function in the output layer, which then is the sum over all k, w, n, k, l, y, k, l minus 1 minus theta n, l minus 1. And here we use usually always the same output functions, activation functions, so it doesn't have an index in itself. And these quantities here are as usual the local fields, B, J at input layer L. Okay, so, and then we train by gradient descent. So our adjustment of the weights in layer L is given by minus eta, the derivative of our energy function with respect to this weight. Okay, so this is our gradient descent equation. So for each of these connections here, which are labeled by Ji in each layer, which are labeled by the L in the subscript, we do this calculation, and from these recursive formulas to calculate how we adjust, how we update the weight at that position. Is that clear? The idea, I mean? Good. So the calculation, as you can imagine, because it's recursively, it's a little bit complicated. And since we are a little bit short with time now, I will skip that. But if you want to know more, you can, for instance, look up in these books. First one in particular, it's written down in detail. But the result is the following. So the result is that delta W J K L is updated by eta, the learning rate, as before, a quantity which I call delta, capital delta JL, Y K L minus 1. And one can do also the same calculations for the thresholds themselves and also update those. So it's a similar start. I take this and derive the H with respect to the threshold, and I get this formula here. It uses the same quantities delta. And these deltas are called the errors in the specific layer and are calculated in the following way. So delta J at layer L minus 1 is equal to the sum over all I, delta L, W, Ij, L, G prime, Bj, L minus 1. Okay. So now it takes a moment to digest these formulas. I will try to explain what they say. So here we have an update rule with the learning rate and these arrows. They are called arrows. And the local state of the neurons in that layer. And the similar thing for the theta. But to be able to update our W's, we need to calculate the deltas. Okay? And the deltas are calculated also from the W's and the derivative. So here's a prime, and that's the derivative of the activation function in a certain layer at a certain position, for a certain neuron. But you see, the important thing here is that if you want to calculate the error in a layer L minus 1, so say for layer 1 here, then you need to know the error in layer L, meaning in layer 2. So actually, you have to start calculating this error from the end of the network. You have to start with the output layer, and this is why you need an initial condition here to actually be able to start calculating these errors. And this is given by Sj mu minus St G mu times G prime of Bj capital L. Yeah, so this is the error at the very end, at the output layer of the network. And this difference here appears because we have it in our energy function. It appears when you do the derivatives. And then from the derivatives, you get the derivative here. And in principle, if you start from that energy function, you get a sum over all patterns here, over all mu. But if you start without taking the sum, just presenting example by example, you get this stochastic gradient descent again, which I mentioned before. So in practice, what you have to do is, if you want to use this algorithm, what you have to do is you have to take one example, x, y, present it to the network, calculate forward all the y's, because you need them to calculate the local fields. And then at the end, you calculate all the errors going backward through the network. Okay, starting from the end with this one here, plugging this into here to get L minus 1, and do that recursively back to the start, and then you plug in all the errors in that in these formulas, go forward again and correct all your delta W's. And this is why this is called error backpropagation, this algorithm. Error backpropagation. Okay, and as far as I know, this is one of the standard algorithms to actually train these networks. Clear? Good. So for the G here, for the activation function, common choices are the following. It's the sigmoidal shapes. It's G of B equal to sigma of B equal to 1 over 1 plus e to minus b, or also the tangents hyperbolicus. So both have basically this shape here, like sigmoids. And the advantage is with those that you can express the derivatives by the function itself, because you need the derivatives here in that formula. So for instance, for sigma prime, you can write this as sigma times 1 minus sigma. And for the tangents hyperbolicus prime, you can write this as 1 minus tangent hyperbolicus squared. So that means once you have calculated all the B's and the G's, when you propagate forward through the network when presenting the example, you can use the same expressions doing the back propagation with your errors without having to do more calculations. It's also important to remember that we actually, you could say, we could simply use a linear activation function. It's even simpler, right? Why not choose just G of B equal to B, like we discussed yesterday, linear activation function. The derivative is constant, very simple. The thing is that then the whole network is just linear. It's like multiplying these matrices, linear matrices, on top of each other. So the whole thing is simply still a linear system, which is then solved exactly the same way as we discussed yesterday, with the same problems, that you have to have examples which are linearly independent to be able to train it. So that's also one reason why you want to have nonlinear activation functions, to get rid of this restriction. Okay, and also if you want to do this training, you need to initialize your W's in the network. And the common choice for that is common choice for the initial W's, L, is a Gaussian distribution with 0 mean and some variance sigma w squared, which is a parameter you have to choose. I will come back to that a little bit later. Okay. Are there any questions about that error back propagation? This does not seem to be the case, so that we can continue a little bit by discussing a few practical aspects if you really want to use that. And some of these practical aspects are connected to problems that actually show up in these settings. Namely, the first one is vanishing or exploding gradient problem. The second one is overfitting. And then we have a few other aspects which are not connected directly to these problems but are still useful. So let's consider the vanishing or exploding gradient problem. What's going on here? So if you look again at these formulas, here's the G prime, and you imagine you calculate this recursively, or you plug in the delta L minus 1 into the next solution, into the next iteration, and do that, you get products of these G primes for the different local fields in the different layers. So G prime of B1 times G prime of B2, G primes of B3. So you have many, many G primes. And if you look at this, these activation functions have regions where actually the derivative here and here is exponentially small. So that means that if you really have many, many hidden layers and you propagate back to the network, it can happen that basically there are many small factors which make the error disappear. Or in other words, at this end, at the beginning of the network, it doesn't really know what happens at the end. It doesn't get the information from the output, doesn't travel back. So if the gradient vanishes, it's called the vanishing gradient problem. And then you can say, okay, maybe I would just try to make the W's large enough so that the product here is 1 or a little bit larger. But then, again, you have many products of these. If they are larger than 1, they explode very quickly. And then you have the exploding gradient problem, in a way. So then your algorithm, the weights explode very quickly, and you cannot learn anymore. So you have to find a balance between these two extremes, or you have to find measures which help you to get rid of the vanishing gradient problem. It can be shown, for instance, that if you choose initially the size of the variance as 1 over the input dimension, then you are in the range where these effects balance, at least in the beginning. So that would be a smart choice. So otherwise, other strategies, what you can do, you can actually indeed use, for instance, different nonlinear activation functions. For instance, the rectified linear unit, which we discussed. So that would be this function here. Looks like that. Because then you don't have that problem that when b becomes larger, that the derivative disappears. So the learning propagates back through the network. And also another advantage is if the b is small, then the output is actually 0. So there are a lot of connections for specific input patterns which may not contribute to the whole propagation of signal and error. So many of these connections might actually be 0 for a specific input pattern, which makes the learning also easier, and also empirically it seems to be more stable in these cases because the network is sparser, it's not so fully connected. So this is one thing you can do. Another thing people try is that they actually jump layers. So you make connections that skip some layer. It's called residual network. So the empirical evidence is that if you create such shortcuts in the network, the learning becomes more stable, and the vanishing gradient problem is not such a big problem. As for instance, you can imagine a network with just one layer of neurons everywhere, one neuron in each layer, I mean, and then you can maybe skip and have connections here as well. Instead of just going from one to the next layer, you jump. And if you do things like that, then the error, if you calculate the error in the same way, it gets extra terms which are connected to these shortcuts. So now the notation becomes even more complicated because I have to tell which layers the W actually connects. So here it's the neighboring layers, it's the standard ones. And this is the same part as we had before. It's basically this part here. And then, I mean, this is just the structure of the equations without the too many indices and so on, because it's one layer only. And then you have the L+1, which connects the layers with which skip one layer. The connections like here. So this is L+1, L-1. This is one that jumps. So you get several alternatives how the arrow can propagate through the network backward. It can take the usual path, or it can jump through shortcuts. And then if you write this down recursively, the arrow that is the most important one is the one that takes the shortest path through the network. And that in that way you can also like work against this vanishing gradient problem because you have less factors G prime in that shortest path. But much of that, what I'm saying is, as far as I know, empirical, so there is not really a theory for that. So if the weights become too large, you also run into that problem that you end up here in that end where the derivatives are 0 or very small. For that reason, another strategy people are using is a regularization procedure by reducing the size of the weights. So you for each weight, you want to reduce it a little bit in each training step so that it doesn't become too large. So that you stay in your local fields in the region here, which is relevant for learning, where actually something happens. And there are several ways to do that, but one possibility is, which is called L2 regularization, that you add in your energy function here, you add a term that actually does that for you. So this is the old one, which is the learning of the training set. And then you add a term which is quadratic in the weights. So that means that large weights are punished energetically. So the gradient descent automatically takes care to keep the weights a little bit smaller. And if you do the calculation, you get an additional contribution in the learning, in the update for the weights, which is the old derivative of this initial part here, and then minus epsilon times wij, which reduces the length of the weights proportional to itself. And the epsilon here, the small parameter, is given by this gamma times the learning rate. Okay, so if you choose an energy function that contains a term that punishes long weights, large weights, you get a regularization in the learning. And you can choose different things here. For instance, if you take the just the absolute values of the weights like that, you get L1 regularization, and you get a correction term which is here in your update, the sign of the wij. Okay, and probably there are many more strategies or attempts, empirical, to deal with these problems, but these are the ones you encounter most when you look for what to do. The other problem I mentioned is overfitting. So what do I mean by that? Remember this sketch here. I will try to illustrate it. Remember that we had this geometrical picture when training. That we had a boundary that separated the different classifications here in the plane. And then we said when we add more layers, the boundary can become more complicated. For just one layer, for the perceptron, it's a line, but it can become more complicated. So it can be really maybe something like that. And you have the different classification, the different labels on the two different sides for the two patterns. So on one side it's -1 here, and on the other side it's +1. But you can already imagine if you have such a fine structured boundary that this might maybe be learning noise here. Because imagine you have a large training data set and you present maybe half of the training data to the network, then the boundary looks in a certain way. But if you present the other half, then the boundary is slightly shifted probably because of the positions of the points. So if the networks trains very specifically the first half of the network, it misclassifies the other one, and this is overfitting. You learn too many details. Okay, you don't learn the general features anymore, or you learn the general features, but also all the details which are very specific for this training set you have, and this is overfitting. So what you can do here in that case is that you actually split your training set into two parts, more or less just like I said. This is called cross-validation and early stopping. So you split data set into a training set and a validation set. And then you start training with just the examples in the training set. But during the training, you at the same time always calculate the energy function. This is our target we want to minimize for the validation set. And then, if you plot or observe typically the logarithm, because h is large, if you plot then these two functions as a function of the number of training iterations, you will typically observe something like that. Let's say the training set is in red. It will probably look something like that. So the energy goes down to its minimum over the training. This is how the algorithm is constructed. And the validation set, let's say in blue, is from the same overall data, which shares the same general features, but is a little bit different in detail. So that means that they will go down as well, but maybe at some point it starts to split, because the algorithm starts learning the specific details in the training set. And then the energy in the validation set will not decrease anymore, because it doesn't share the specific features. So, and then you can say, okay, if this starts to happen, maybe here I can stop my learning, because I'm starting to overfit. I can see that from these curves. Okay? And yeah, for these kind of strategies, you typically need lots of input data. So somehow you always need to have many data. But then there are these restrictions, like Oliver said. You don't want to be in the lab for weeks or months to produce data. So there's always the balance to find. Yes, a few more practical aspects that are of more general nature. So one thing is what you should always do is pre-processing the input data. Maybe you want to reduce the dimension to start with, using net core. I'm advertising your algorithm now. Or also an important thing is standardization. So that the different dimensions in the feature space look similar, that you don't have one dimension where everything is very large and another dimension where everything is very compressed. So what one typically does is to move the average of the input data for each component I, meaning for each dimension, to 0. So you average over all the input examples and you set this to 0, I mean by a shift of the input data. And likewise, the variance you want to move your data such that the variance is equal to 1. And this has a kind of smoothing effect on the energy landscape because the different dimension become comparable so that the gradient descent learning becomes easier. Another strategy is to average a little bit over the data during training by presenting mini batches, it's called. So not just a single example in every training iteration, but a number of examples. And then average over them. So you would update your weights not by using one training example, but by using an average over a small mini batch of examples. So now these quantities here get indices mu for the training examples. So you take this, we had here somewhere here, and you average over a small number of training examples. This seems to be working quite well in comparison to single ones. And then sometimes you have in the energy landscape, you might have regions where the gradient is very slow, where you can get stuck for a long time. And this can be treated by the adaptation of the learning rate by giving it some momentum the following way. This is called, it's indeed called momentum. So you keep up the speed a little bit. If you have the update at a certain time t, you do that by calculating your gradient at that time t, but you add a small step which is from the previous time. So you reuse your update from the previous time step and add it with a small parameter alpha. So if you are moving downhill in the energy landscape and you reach into a flat region, there's some memory that carries you on, hopefully, in that direction. So if you recursively write it down, you can see that if you do that, the update at a certain time point is the weighted average of the update of all the previous time points. So there's some kind of memory or momentum in the system that you exploit. Another strategy is that when you learn and you see that some of the weights are close to 0 during learning, then you can actually throw them away. So you can take away connections that are not used in the training. It's called pruning, and also the neurons that are not used. So the network becomes less densely connected, and empirically one see that if you do that, then the learning becomes better. And also you can follow a slightly different strategy, that when you present a certain example to the network, then you randomly deactivate certain connections, a number of connections for that example or for that mini batch, learn the remaining connections, and with the next training example, you deactivate another set of connections. And this mimics somehow in several training attempts in parallel, because you train parts of the network by randomly switching off certain connections. So you see, this is called dropout during training, the last thing. So in dropout, the connections are removed temporarily for each example or mini batch, and in pruning, they are removed permanently when you see you don't need connections. Yeah, I mean, there are certainly many, many more strategies you can come up with, or that people invent to counteract the disadvantages of certain training algorithms. But I just wanted to give you a flavor of the most basic ideas. Are there any questions? Yes? Yes. Yes. So, our learning rate at time t is the learning rate at t-1 plus the correction at time t. Okay? And this you do iteratively, each time step. And now, this is what we have done before, just the gradient descent. But now we add the one from the previous time step, and this enters into that. So the update here at from time t-1 to t also depends on earlier updates. Does that answer your question? The learning rate is here, yes. That is not changed. And this is... No, you don't change this value, but you add, this is also like a second learning rate. It weighs in how much memory you have compared to the learning rate. So these are two parameters that are acting relative to each other in that case. So now I have to make a decision, because I was planning to present like two other network architectures which are used for modern tasks nowadays. Just to explain a little bit how they work, namely convolution networks, which are used in image recognition, and then also recurrent networks. But I think I'm running out of time, because I also spontaneously, after question yesterday, I wanted to show you something on the computer, which is probably much more fun than continuing on the blackboard. So I guess you want to see the thing on the computer, right? Okay, so the question was I got from some guys here, some participants, is can we do some coding with that? And I haven't thought of that, but actually then I remembered I was a student in Germany, in Würzburg, where I studied physics, and at that time, long ago, there was Professor Wolfgang Kinzel who was actually working with the theory of neural networks. I mean, he was doing like perceptron stuff and tree-like networks. And someone in his group, I don't remember who it was, maybe it was actually Michael Biel, he was actually in Wolfgang Kinzel's group as well, before he moved to Groningen, wrote a program for a simple perceptron that can predict what you're doing. And I found this program on my laptop this morning. I was trying to find it, and I still have it. And I will show it to you now. And my suggestion is that you try to program something similar if you want to. So do you see that now? Yes, perfect. So this is in German, fortunately. So what you see is the perceptron. You recognize that, right, in the beginning. You have, I think in this case, it's 8 or 10 input units. And they are all in red. And then there is the output unit in blue. And then red means the neuron is active. Green means the neuron is silent, inactive. And you also see how strong the weights are. These are the bars where there is Kopplungsstärken. So these are the connection weights. It's how strong they are. And what you can do now is you can type 1010, and the network is trying to predict what you're going to do. So if I start typing 1010, so you see they're coming in from the left side. So everything that is I type in is presented to the network and the leftmost neuron and shifted to the right all the time. So I do this, and then the network tries to predict what I'm doing. Now I'm giving a pattern, just 1 plus 1 plus 1, also 1 0 1 0, and you see the rate with which it can predict what I'm doing is 90% right now. So it's still in the beginning it was wrong because it didn't train the pattern yet. So it's still counting in that. And then you also see that actually for this simple pattern, it only needs 3 weights. All the others are actually 0. It's there. A laser here maybe. No. So you see in the beginning, it's just these weights that are used, not the other ones. Now I can change the pattern, say 1 0 0 1 0 0 1. So now you also see that it also says prediction falsch, also Vorhersage falsch is prediction incorrect, Vorhersage richtig is prediction correct. So you see it, after some time it has adjusted the weights and it can predict what I'm doing. And I can now try to actually be as random as possible and get down the prediction rate to 50%, so that it's impossible for the network for me, but it's actually difficult to be random. So this is, and you see how it learns all the time. The weights are adjusted, and depending on the input pattern. But now another thing that's also very interesting is that you can actually kill certain neurons in that program. So there is a lösche neuron. If I press L, so it asks me to lösch, to delete, say 4. So this is now deleted, and then I can see how that influences how it predicts what I'm doing. This is not updated anymore. And you can actually play around. I do a reset now. You can play around, but this is too simple. So you can play around and delete after some time and see that sometimes it does not actually change much of the prediction rate if you delete one of the neurons. So they are actually also quite robust, you can see. So if something goes wrong, if one weight or a few weights are screwed up for some reason, they still can do their job. So I invite you to program this in Python. I'm not a big Python programmer, so I don't know about the graphics, but it's probably not too difficult. And the algorithm per se is very simple. It's what we discussed yesterday. It's a Rosenblatt learning algorithm. So you can try to do that and see if you can produce such a program. This here, I said I didn't write it. This here uses the X window library on Mac, so it was a little bit difficult actually to get it to compile. Last time I looked at it was 20 years ago, so I had to convince the compiler to do it. But yeah, you see it's working. So I guess doing something like that in Python is not too difficult. Yeah, I'm here for the rest of the week. If you're interested and want to try it, yeah, you're welcome. We have the afternoon working hours, not today, but then tomorrow and I think on Friday as well. So we can have a look together also if you want. Are there any more questions? Yes. In matrices, yeah. For a line, you mean? In the plane? I don't understand how you mean. Aha, yeah. Ah, okay. So now this here, it's only predicting the next output. It's just predicting one value, not the whole line. But I feed in the whole line. I shift it to the right. So I'm not sure if I understand your question correctly. But you can, I mean, if you're thinking about you want to learn matrices and so on, this you can do, yeah. You can extend it to that. More questions? Okay, then lunch break. See you after that.